This is the third in a series of videos in which I'm attempting to develop a solid-state memory replacement for the Fluke 9010A cassette drive. I mentioned in the previous videos that the cassettes are becoming increasingly difficult and expensive to get hold of, and so what I'm aiming to do here is to create a replacement, a direct drop-in replacement for the cassette mechanism. And I went through in the previous couple of videos the various options that I had, and what I've decided to do is to create a replacement for the entire cassette mechanism. As you can see, I've popped it out of the top cover here to give myself a bit more space. And what I want to do is develop a small add-on board that will effectively allow connection to the main unit through the ribbon cable to the same port, and so it will have to duplicate from the perspective of the 9010 the functionality of the cassette mechanism and control circuit. The cassette itself consists of a control board, and there's an interface IC on here. It's actually a microprocessor. There is code running in this, so the 9010 just sends a command and data to the interface IC, and the interface IC is then responsible for the timing and control of the actual mechanism for reading and writing data from and to the tape. So what I've done so far is look at the general circuit and figure out the best approach for this. And so what I've done is I've written a disassembler for the code within the IC. I did initially try using a disassembler that I'd downloaded off the internet, but it didn't really work very well, so I ended up writing my own. And the output from that, I've been going through and I've started to annotate it. And so I won't go through this in too much detail. You've seen me do this before, but really what I do is I go through, I start at the reset vector, follow it through, annotate the code, break it into blocks, lots kind of logical blocks as to what each particular part does. I start adding text to further explain and clarify what the various blocks do. And what I end up with, in theory, is the source code for the firmware. And so, as I've been going through this, what I'm really looking for is the parts of the code that I need to retain. So, for example, we have sections like this where we have a block here that's it's just a delay, so the R3 register is loaded with a value, this function's called, and it loops around the number of times based on what was loaded into the R3 register. And then the next one down, the next block down, is also a delay loop, but it uses the timer built into the IC. And if I keep going through the code and trying to disassemble it, then what I end up with are blocks of code like this, and then going through and trying to figure out which pins on the device the code is controlling and what's going on. Then I can usually figure out what the block of code does. So for example, this particular block of code reads a byte or reads data from the tape drive when it's running, and it shifts it into the R2 register in such a way that it effectively reads a byte of data from the tape and decodes the various ones and zeros that are encoded onto the tape, and the next block does the reverse and it writes a byte to the tape. Now of course these blocks we won't need because we're not going to be encoding anything as such on the memory chip. We're just going to be writing the byte value that was in R2 at this point into the memory chip and then reading it back when we come to read the tape. And so what I'm doing is going through and trying to figure out all the blocks, and it's specifically the interface instructions, commands to and from the 9010, so that I can create a drop-in equivalent that behaves in the same way from the perspective of the 9010. Now what's going to really help me with this is to hook up the logic analyzer. Now I've got this far. What I want to do is to hook up the analyzer and then start examining the various behavior to make sure that I've properly interpreted the firmware and that I know what I'm doing when I come to writing my own code for the microcontroller that I'll be using. So what I'm going to do is hook up the logic analyzer. This is the pinout for this device. I don't need to hook up the logic analyzer to anything else at the moment other than the pins on this device. So I'll hook up all the relevant pins. So we'll be looking at the sort of reset, chip select, data bus, and the port 1 and port 2 pins. I'll also need to hook up one of the clock lines. As ever, I'll run the analyzer in state mode to make sure that we get kind of a one-to-one correlation between what we're seeing on the analyzer screen and the clock cycles of the device itself, because that, after all, is what I'm trying to duplicate. So I'll get this hooked up, get back on camera, and then we'll do a bit of investigation and start looking at how the hardware is behaving relative to what we've seen in the firmware. Okay, so I've got the logic analyzer hooked up. I've connected it up and given the analyzer probe pins names that match what's on the datasheet, and we'll have a look at the logic analyzer screen. There's nothing really much I can show you on the Fluke itself. All I'll be doing here is powering it up and then using the tape read and tape write keys and functions to activate and access the tape drive mechanism. But what we're trying to look at here is the way that what we see on the analyzer relates to what we're seeing in the firmware listing, so that I can further deconstruct this and then use what I end up with to write new code for a microcontroller that we can ultimately plug into this port. So I'll move the camera, we'll have a look at the logic analyzer screen, I'll show you how I've got it configured, and then we'll do a few basic captures, and then in the next video we'll do a bit more in-depth testing to investigate the firmware. Okay, so I'm using my Agilent 1670G, and I'll just quickly run through how I've got this set up and configured. As ever, I've created a separate directory to hold the configuration. And firstly, what we have is I've only selected currently one pod. There aren't that many pins, of course, on this. It's a single IC. If I need to, I can just use one of the other pods later. But note that I've got the analyzer set to state mode. So in other words, we'll be using the Fluke cassette chip clock to drive the analyzer rather than have it free running in timing mode. Looking at the configuration for the individual pins, then what I have is data, and of course all this relates directly to the format in the datasheet. So all the pin names on the datasheet, as much as possible, I've tried to use here. So data is the data bus that's connected to the Fluke 9010, and then we've got all the control lines, so chip select, reset, etc. We can examine all those and see exactly what the device is doing. And then going further down, the second pod I'm using just to monitor the two ports, and the ports are on the cassette hardware side of the 8041 device. So as we go through this and look at the firmware, I'll obviously be referencing the schematic for the cassette mechanism, so we can see what each of these pins is meant to be connected to. And we may even change the name of some individual pins. So for example, although we're looking at the entire port values here, the individual bits control specific functions. So for example, we could rename one of the bits as forward and one as reverse and that sort of thing for their actual function on the cassette mechanism. But to start with, we'll leave it like this. We can always make these more meaningful later. And on the waveform display, I've just selected all of the waveforms, all the pins that have been defined. And then for the trigger, at the moment, as simple as possible. So I'm just monitoring the chip select pins. So anytime the Fluke 9010 tries to access the tape drive mechanism, then we should be triggered. Again, we can look at this in more depth once we know what the individual values are that the 9010 is writing to the cassette. So if we go to waveform, we can now arm this. I'll turn the Fluke on first, so it's booted up. So the Fluke is now running. We'll arm the analyzer, and if I now press one of the two tape keys, tape read or tape write, then we should be triggered, and indeed we are. So at least we know that we are hooked up and we're able to access the tape drive, and from this point on we can start doing specific testing to see how the individual functions work within the tape drive system itself, and what the actual command values are that are being sent to it from the Fluke. For example, it's checking to see if there's a tape present, whether or not it's at the end of the tape, this sort of thing, and we can see what particular commands and return values are required, and they are what we will need to program into our replacement controller. Okay, so in the next video we'll go through some of the code in more detail, do some proper investigation with the analyzer, and hopefully get a lot further resolving the firmware so that it can be fully annotated and we can pull out the parts that we require and start writing a control flowchart that we need to duplicate in our replacement device.